Bismillahirrahmanirrahim. So, welcome to the second lecture about the redox stability at non-standard conditions. So, let's start the lecture. This I have already discussed in the previous lecture. So, moving to the second lecture. Actually, based on the previous lecture, now you can apply that knowledge to check the stability of the redox species, either the oxidizing or the reducing. So again, let's start with these are, I have just mentioned here the two examples, A or B, maybe the any metal ions. So you can take any metal ions, you can take any one of the half cells from the electrochemical series. So as an example, I have mentioned here A plus 2 accepting one electron forming A plus, and similarly this is the oxidized form accepting one electron going to be reduced, which is the B plus. And let's suppose this is having the standard cell potential of 1.2, and this is for the B is 1.3 volt. So again, if you want to, in this way, I'm just going to check the stability of A plus 2 or B plus 2 in water. So as we have already discussed, if you want to check the stability of the A plus 2 or B plus 2, or in general, these are the oxidized form. So you should take this half cell of the water because these are the oxidized, and this will be the water which are going to react with these metal ions. So it is very simple. You just have to check the possibility either A plus 2 or B plus 2 are going to react with water or not. So it is a simple way is you just calculate the cell potential, which is the cell is the cathode minus the anode. So it is the 1.23 minus 1.2 minus 1.23. Cathode is, in this case, in case of the water, it is 1.2. And this half cell, you, as we have already discussed before, you should take at the anode. And this standard cell potential is 1.23, and this will be equal to minus 0.03 volt. So that means it is the minus is indicating that this is the non-spontaneous reaction. Non-spontaneous mean A plus 2 is stable in water, or water is also stable in the presence of the A plus 2. So these are the standard conditions. So let's move, this I have already discussed before, and you have submitted the assignment over there. So let's move to the B plus 2. B plus 2 is in similar way. The standard cell potential is 1.3 and minus 1.23 is the standard cell potential of the water, and it is the net cell potential is 0.07. So this is also standard cell potential of the direction. So this plus is indicating that B plus 2 is unstable in water, or water is unstable in the presence of the B plus 2. So at the given condition, A plus 2 is stable and B plus 2 is unstable at standard conditions. So let's move to the non-standard condition. This is very important. So for the non-standard condition, let's suppose if the pH is 3, that means you first have to calculate the cell potential of water at pH 3, and you can take this formula. You can use this formula as we have derived before. It is E is equal to 1.23 minus 0.0591 pH. At pH 3, the value will be 1.052. You can calculate by putting the pH over 3, and then this is just multiply and minus. It will give you the value of 1.052. So what is it is indicating? Again, you have to calculate the cell potential. It is the cathode minus the anode. This will remain the same because A plus 2 plus 1 electron forming A plus 1 doesn't having the hydrogen ion in its half cell. So the pH is not going to change the potential of the uh, A plus 2 ions. So only the pH is only affecting the potential of the water because the pH over here, and at pH 3 now the potential is 1.052, and if you minus this one, the value is plus 0.147. So you just have a look on this one. A plus 2 was stable at the standard conditions. So when you change the conditions to make it a non-standard conditions, that means at pH 3, the cell potential becomes positive. That means A plus 2 becomes unstable at pH 3. And this is very important. That means you can change the stability of the metal ions by just varying the pH of the solution. So let's see what is happening with the B plus 2. Similarly, you can also calculate the cell potential of B plus 2 with the water. Again, this will remain the same because there are no involvement of the hydrogen ions in case of the half cell of B plus 2 to B plus 1. And only this is going to change, and this we have already calculated in case of the A plus 2. So the value will be plus 0.248 volt. So B plus 2 is again unstable at pH 3. So B plus 2 was unstable at standard condition and also unstable at pH 3. So, but even it is more unstable as compared to the standard conditions because the potential is more positive as compared to the standard conditions. So this is the way you can calculate the cell potential, and you can discuss the stability of the metal ions at non-standard conditions. So let's see another example. So these are the oxidized form. Now I am going to discuss the reduced form. So when you discuss the stability of the reduced form, you have to take this water half cell as a reference at the cathode. So stability of C plus 1 in water at standard condition. Just look at first at standard condition and then we move to the non-standard condition. Again, you can calculate the cell potential E cathode minus E anode. E cathode in this case is the minus 0.833 volt because this half cell is going to reduce and reduction must be at the cathode, and this is going to be oxidized. That's why I have taken minus 0.7 at the anode. And if you solve this one, because this is the minus multiplied by minus become plus, and the net result will be minus 0.133 volt. So this is indicating that C plus 1 is stable in water, or water is also stable in the presence of the C plus sign. So now move to the non-standard condition. So as a reference, I am just using different pH. You can use any of the pH to decide the stability of the metal ions in the presence of the water. So in the pH 7, that means it is a neutral water. So actually this is the water you are going to use at the laboratory, and it is not the standard condition. These are the non-standard conditions because the pH is 7. That means the hydrogen ion concentration is exponent minus 7, not it is the unit concentration. So let's first calculate the potential of water at pH 7, and this we have already discussed in the previous lecture. You just use this equation, put the value of 7 here, and then calculate the overall value, which is minus 0.413 volt. So for C plus 1, E cathode minus E anode, you just put the value and the whole number is plus 0.286. which is indicating that C+2 is unstable in water, and the water is unstable in the presence of the C plus ion. And this was you have to mention the condition that this is at non-standard condition and pH 7. And you can check the stability even pH 2 or pH 8 or pH 14. It depends on your interest to further explore the stability of the metal ions in the presence of the water. So A, B, or C, these are the oxidized form or the reduced form of any metal, which you can take any of the metal from the electrochemical series. So this is all about the stability of the metal ions in the presence of the water at non-standard conditions. So by changing the pH, in case of the C plus 1, it was stable at standard condition, but it is unstable at non-standard conditions. So this is the importance of this lecture. As a chemist, you can decide the spontaneity of the reaction just by changing the pH of the solution. So for your assignment, this is your assignment. So you have to check the stability of the zinc plus 2, iron plus 2, sorry, this is the iron. It is mistakenly written as the fluorine. Iron plus 3 in water, both at standard conditions and at non-standard condition, that means at pH 8. So this is at standard condition you have to check, and you have to check at pH 8 in the similar way which I have already explained to you. That means you have to check the stability of the iron plus 3 and zinc plus 2 in a similar way which I have explained over here, A plus 2 or B plus 2, or you by comparing with the half cell of water, which is 1.23. And then you have to explain the stability of the iron plus 2 or the zinc. And this you have to compare with the water, like in case of the C plus 1. So reference are given above, and these half cell are given here. This is very simple. You can also do some other exercise at home. So you will learn a lot out of these calculations. So these are really applied in nature, and this exercise will help you to understand the electrochemistry in detail. And of course, you will be using in your research work as well. So thank you for watching, and we will move to the another lecture soon. Thank you very much.